Out-of-memory error exceptions can occur due to the finalization as well. Let's look in detail how this might happen and how we can troubleshoot if a memory issue is caused due to the use of finalizers. Out-of-memory errors can also be caused due to the excessive use of finalizers. Objects with a finalize method may delay their own garbage collection. The finalizer thread needs to invoke the finalize method of instances before those instances can be reclaimed and their heap space is freed. When the garbage collector determines that an object with a finalizer has become unreachable, it adds it to the finalizer thread's queue. Now, if the finalizer thread does not keep up with the rate at which the objects are added to its queue, the JVM might fail with an out-of-memory error, even though the objects piled up in the finalizer's queue were eligible for collection. Therefore, it's really important to make sure that we are not running out of memory due to a large number of objects pending finalization. I would also like to mention here that the finalizers are being deprecated in Java 9. Let's talk a bit about the useful diagnostic data and the tools that can help us with this problem. Information about the objects pending finalization can be obtained using tools JConsole and JMap. We can extract this information from heap dumps as well. This is a snapshot of JConsole connected to a live process. The VM summary tab shows the pending finalization object count. In this case, this count is 0. But if this number is high, then that's a strong indication that the Java heap and the native memory resources might not be getting released promptly, and that could lead to out-of-memory situations. This snapshot shows finalizers related information extracted from a heap dump with Eclipse mat. This shows the objects that are being processed by the finalizer thread and the ones that are ready to be processed. This also displays details about the finalizer thread itself. Information about the objects pending finalization can also be extracted from a heap dump. This snapshot shows a heap dump being explored with the visual VM. As learned in the previous lessons, PermGen or MetaSpace is the memory pool that the JVM uses to store the classes and class metadata. In this segment, we'll cover how we can troubleshoot class and class loader related memory issues. Now, before we start investigating the causes of memory leaks in PermGen or MetaSpace, we should first confirm if there is a memory leak. We should monitor the usage of the PermGen or MetaSpace over time. If there is continuous memory growth and there are frequent full GCs after the application has reached a steady state, and those full GCs are not able to claim any space in the PermGen or MetaSpace, then it could just be a configuration issue. It might be just that these spaces are sized too small. We should increase PermGen or MetaSpace size and test the application again. If that does not resolve the issue and we still see continuous memory growth and encounter out-of-memory errors, then that suggests the possibility of a memory leak. From these logs, we can see that full GCs are occurring to free up space in the PermGen, but no space is getting reclaimed. That could mean that the PermGen is sized smaller than the application's requirement. This snapshot shows growth in the MetaSpace usage over time. But with every full GC, the usage drops to around 10 megabytes. While this type of behavior may not directly lead to an out-of-memory error, it may indicate that the application is unnecessarily loading and unloading the same classes again and again. As this may represent an opportunity to improve the performance of the application should probably be investigated to understand why certain classes are continuously being loaded only to be unloaded during the next MetaSpace collection. To configure the size of the PermGen, we can use perm size and max perm size options. Perm size sets the initial size for the permanent generation, and the max perm size option sets the maximum capacity for the PermGen. To configure the size of the MetaSpace, we can use the MetaSpace size and max MetaSpace size options. MetaSpace size sets the initial size for the MetaSpace, and the max metaspace size option limits the maximum size of the metaspace. If max metaspace size is not configured, then the JVM is free to use all of the available native system memory for the metaspace. As we had seen earlier, in 64-bit JVM, the metaspace has a separate logical region called the compressed class space. If the JVM option use compressed class pointers is enabled, then we have this separate area for the class metadata. Use compressed class pointers is enabled when compressed OOPS is being used. On 64-bit platforms, compressed OOPS is enabled by default. With this option, a subset of the class metadata is stored in this separate memory pool, and the class data it holds can be referenced by a 32-bit offset as opposed to a full 64-bit pointer. By default, 1 GB is reserved for the compressed class space, but this can be changed with the compressed class space size option. The maximum value that we can set for the compressed class space size option is 3 GB. The JVM option max metaspace size that we talked about in the previous slide sets a maximum limit on the combined committed sizes of both the compressed class space and the rest of the metaspace. This is an example of the GC log entry showing the committed size for the whole of the metaspace as 4864 kilobytes, which includes the compressed class space for which the committed size is 512 kilobytes. As mentioned in the previous slide, max metaspace size is the upper limit on the committed size of the total metaspace. Let's say if the max metaspace size was configured as 512 megabytes, then the total committed size listed in the first line of the log entry here could grow only up to 512 megabytes. Let's see what diagnostic data and tools can help us troubleshoot memory issues in PermGen or MetaSpace. So which diagnostic data can give us insight into what's going on in the PermGen or MetaSpace? The first one on the list is GC logs. Logs collected with -verbose : class or with trace class loading and trace class unloading options prove to be really helpful. They can show if the classes are getting loaded and unloaded as we expect them to, or if they are getting loaded from the correct jar or package. Data collected with JMap, JMap-PermStat for permanent generation, and JMap-CLStat for metaspace provide very useful insights. And of course, heap dumps are helpful here too in investigating classes and class loader related leaks. Class statistics information collected with the gc.class_stats diagnostic command, which you can run with the jcommand command line tool, provides valuable information about the class loaders in use and the number and sizes of classes they have loaded. Java flight recordings also are very helpful in investigating class and class loader related leaks. While investigating the memory issues related to the spaces holding classes, it is very important to make sure that the classes are getting unloaded appropriately. Make sure that the option -x no class GC is not in use, as it will prevent the classes from getting unloaded. And if we are using CMS GC with JDK 6 or 7, we should make sure to enable CMS class unloading enabled to ensure that the classes get unloaded during the garbage collection cycles. This example screen shows the output generated with -verbose : class option. From the class loading information, we can verify if the classes are getting loaded from the right package or jar file, and that any temporary classes are getting unloaded during the garbage collections. This example has a GC log that shows that the last full GC happened because the metaspace had reached its threshold limit. But the metaspace here does not seem to be full at all. The metaspace capacity is at around 6 gigabytes and its occupancy is only at 4 gigabytes. Now if you look at the error message, it says Java lang out of memory error compressed class space, which means that even though there may be room available in the metaspace overall, the compressed class space region of the metaspace has run out of memory. So in this case, we need to see if the compressed class space is configured appropriately and if the classes are getting loaded and unloaded as expected. JMap-PermStat presents class loader statistics, which includes class loaders, number of classes loaded by those class loaders, and whether those class loaders are dead or alive. It also tells us the number of intern strings present in the PermGen and the number of bytes occupied by those loaded classes and their metadata. All of this information is very useful in determining what might be filling up the PermGen. Here's a sample output displaying all of these statistics. We can also see the summary on the last line of the listing. Since Java 8, jmap-clstat prints out similar information about the class loaders and their liveness. But this command displays the number and size of classes loaded into the MetaSpace instead of the PermGen. Heap dumps help here too. Heap dumps are helpful in troubleshooting PermGen and MetaSpace memory problems as well. With the heap dump analysis tools, we should look for classes that should have gotten unloaded but didn't. EclipseMat offers a very nice feature called duplicate classes, which displays any classes that were loaded multiple times by different class loader instances. Now, some finite number of duplicate classes loaded by different class loaders may be part of the application design. But if they keep growing over time, then that's a red flag and should be investigated. This scenario is most common in the application server hosted applications that run on the same underlying JVM instance and are undeployed and redeployed multiple times. If the undeployment of the application does not release all the references to the class loaders it created, the JVM won't be able to unload the classes loaded by those class loaders. And the new deployment of the application would load a new set of those classes again with a new class loader instance. Here's an example showing the duplicate classes view in MAT. This shows that JAXB generated classes are loaded multiple times by different instances of JAXB class loaders. In this case, the issue was the presence of two different versions of JAXB libraries in the class path that caused JAXB classes to be loaded multiple times by different class loaders. And this problem was fixed by using the correct version of the JAXB library. And that brings us to the end of this section. Thank you.